from Harvard University, who will tell us about quantum mechanics.
Okay, thanks, Julian. All right. So today's talk will be a gentle introduction to some problems in condensed matter physics, especially the difficult problems for which the hope is that methods from gauge gravity duality will teach us something genuinely new and maybe ultimately, as many questions this morning asked, lead to some understanding of experiments, but we're still a long way from there. And here, my purpose here is to introduce the difficult problems and present a few challenges that one can reasonably hope string theory and string-inspired methods will be able to meet. All right, so let me just begin with a 10-minute review of solid-state physics. So all of the textbooks in solid-state physics can be summarized in these few lines, starting with the work of Sommerfeld and Bloch. The idea was to just take the electron theory of quantum mechanics and combine it to lead to a description of metal insulators and now today even superconductors. And the key idea of this theory is to just think of the electrons as essentially independent particles. So you start from simple one-electron states and then adiabatically turn on interactions, and as long as nothing drastic happens, you reach an interacting electron state, which experience has taught us describes many experiments very well. So for insulators, you have a bunch of states and you occupy all of them in a given band. This you can only do when there's an even number of electrons per unit cell. Then there's an energy gap to all excitations for a fixed lattice, and that explains the fact why the conductivity is so small. Then in the metal, you have a so-called Fermi energy that separates the occupied states from the empty space states, and excitations across the Fermi energy cost very little energy, and that's why it's possible to have metallic conduction. So this is a one-electron state, but there's of course a much more sophisticated theory of how interactions affect the states. But the underlying principle of that theory is one of adiabatic continuity, that the excitations or so-called quasi-particles of the state are in one-to-one correspondence with the quasi-particles of the interacting states, and modulo some corrections from the interactions, you get the basic physics right in the independent electron picture. So this picture also leads to a good description of superconductivity with just one small twist. You have to think of the electrons pairing and forming a boson or a Kupo pair, and the condensate of those bosons. So now the bosons are sort of independent particles, and if you just condense all the bosons, then you get a reasonable description of superconducting states. Okay, so that's a whole course in quantum many-body theory summarized in 3 slides. So what we want to look at are the modern phases of quantum matter. So I'm not going to say much more about those phases because, well, go and read the textbooks. And one-line description of the modern phases are phases that are not adiabatically connected to simple one-electron states. And these are the states we want to understand more about. And one common buzzword these days is that these states have many-particle quantum entanglement, in the sense of the entanglement that Einstein, Podolsky, and Rosen talked about as a generic feature of quantum mechanics, but here it's manifested in many-particle states. Now, defining and quantifying entanglement in many-particle states is still a wide-open problem. So here I'll just take entanglement to be, as an operational definition, is that property which prevents it from being connected to the independent particle states. That's my definition of entanglement, if you wish. Okay, so we want to understand and classify phases of quantum matter with many-particle quantum entanglement. So we're a long way from that classification, but let me attempt at least some division into different classes of states so that you get a global perspective on much work that's been going on in condensed matter physics. So that's the challenge, and so for simplicity, for this set of lectures, we'll just throw out the lattice, and even in a continuum, there are interesting sets of possibilities of different sorts of infinite quantum systems. So one simple classification, which is useful to keep in mind, is to just classify the states by the nature of the excitations with vanishing energy. So the simplest states are one that have no low energy excitations at all, so gap systems. So the gaps, this is for an infinite translation invariant system, there's a gap to all excitations. So that we'll think of as gapped quantum matter. Then there are so-called relativistic systems where there are zero energy excitations only at selected points in momentum space. Usually k equals 0, but could be a discrete set of points in the Brillouin zone. And often the dispersion near this point is that of a massless Dirac particle. And so there's an emergent relativistic structure that often emerges. And in some cases, even a full conformal structures. And I'll talk about this not today, but I think in one of my subsequent lectures if time permits. And so this we can think of as conformal quantum matter. So here there's naturally some connection to conformal field theory and therefore to anti-de Sitter space anyway. So you can see where these methods might help. And finally, the most interesting and most challenging problems, which probably have to do with the largest number of experiments, are what I'm going to call compressible or sometimes metallic systems. And one definition, at least for now operational, is these have many, many more low energy excitations. So the idea is to find states which have many more low energy excitations than any relativistic system, which has only a single point at which energy vanishes. And in fact, the simplest states of condensed matter, you can find states where the zero energy excitations are on a d-1 dimensional surface. Now, if you have translation invariance, that's a sphere usually. So in 3 dimensions, that'd be a 2-sphere. And so everywhere on a sphere, you have vanishing excitations with vanishing energy. So we'll see why these are what's needed to make systems compressible. Okay. So this is one way to divide the discussion in my lecture. So just to give you some examples then, under gapped quantum matter, well, we have various kinds of Mott insulators and spin liquids and quantum Hall states, which I'll say a few modes about. Then the main part of today's lecture will be on compressible quantum matter with metals and superconductors, which you roughly understand. But the challenge is to understand what I'm going to define this word, at least for my purposes, strange metals. And then conformal quantum matter I'll eventually get to in one of my subsequent lectures. And there are many nice realizations now in ultracold atoms, at least theoretically in various antiferromagnets. But graphene is kind of a trivial example of a conformal system, just a free conformal system. We certainly don't need ADS-CFT methods to understand the basic aspects of graphene. Okay, so now ADS-CFT methods, gauge gravity duality, have had quite a bit of impact, I believe, in our understanding of these two classes of systems, but almost none on this. And we'll mention the reason for that in a minute. But let me just begin by just getting this out of the way, because many of you are not condensed matter physicists. You hear a lot about spin liquids and quantum Hall states. So let me just give you a few examples and the basic physics of gapped quantum matter. So this is a systems with complete gap to all energy excitations. So the most trivial example of gapped quantum matter is, of course, just an insulator, what I call a band insulator, where just every single particle state is occupied, and that's gapped. But we want something more non-trivial, and so you can get non-trivial examples. Example is what's called a Mott insulator, where you have an odd number of electrons per unit cell. So notice now I haven't drawn a simple band picture because it doesn't apply anymore. The band picture would tell you that in the Sommerfeld block theory, that's one of the conclusions of Sommerfeld block theory, that anytime you have an odd number of electrons per unit cell, it must be a metal. But that's not true. But if you allow for interactions, you can get non-trivial phases in which you have an odd number of electrons per unit cell, but nevertheless you're an insulator, and that's what you call a Mott insulator. And really the first clear-cut and best understood example today is this picture of, say, electrons in a triangular lattice. So there's one electron on every site, spin a half on every site. The charge is localized, but the electrons form singlets or valence bonds with their nearest neighbors. So this is a structure very similar to a pi bond in benzene. And just like in benzene, then you have resonance between different configurations, and so you have what's called a spin liquid, or the resonating valence bond state, in which there's no broken symmetry. There can be, under certain conditions, a gap to all excitations, and it's an insulator. So this is a state that violates, the Bloch, one of the main, the hallmarks of the Bloch theory of independent electrons, and so we call this a mod insulator or a spin liquid.
Is it known this is the ground state of the Hubbard model?
Oh no, of course not. But I think, well, let's see. Okay, there are now certain, not precisely the triangular lattice. There is, I guess, the best example of this kind of gap state would be now the J1, J2 model in the square lattice. So there are numerical studies of various model systems in which there is, I think, reasonably convincing evidence that such a state exists. And there are, a number of other less realistic systems for which you can essentially prove that such a state is possible.
It's believed for the triangular lattice, is this the ground state of the Hubbard model?
I think that's an open question at this point. For precisely the Hubbard model, we're not quite sure. In fact, the bet is probably not this if you go by recent experimental studies. There's another possible spin liquid state, which in fact I will turn to a bit later today. Okay. So what are some of the unique properties of this state? Well, one of it is the idea of topological order. It has topological excitations that, again, have no analog in the one particle system. And one of those, in fact, in the simplest so-called Z2 spin liquid, is sometimes called a Vizon, and it's a vortex in this sea of singlet bonds, where you pick a point, and that's this particle. So it's an analog of a vortex, and you make a branch cut starting from this central point, and you have some superposition of these singlet bonds forming your, entangled many-body wave function, and you change the sign of just a small number of terms in that infinite sum of valence bond configurations. You change the sign on any for every bond that cuts this, that crosses the cut. So for this particular configuration, you'll pick up a -1, whereas others that you don't have any even number of bonds crossing the cut, you wouldn't pick up a -1. So that's a vortex-like state, and it can be shown to be stable, cost of finite energy, and so there's a whole new sector of excitations which have no analog in a band insulator. So one consequence of this kind of Vizon is that if you now take this system and put it on a manifold of non-trivial topology, for example, a torus, then you get ground state degeneracies. So if you put this Vizon now in the whole of the torus, then it costs essentially no energy, and whether you put the Vizon or not, then you get orthogonal ground states, and so you have an additional degeneracy depending on the topology of the manifold, and that's why this is sometimes called topological order, associated with this example of gapped quantum matter. In this case, you can put the Vizon either in this hole or the other hole of the torus, and so for the simplest Z2 spin liquid, there's a fourfold degeneracy. So what is known is that essentially all the known classes of such gapped quantum matter are described at low energy by some kind of Chern-Simons gauge theory. So this wouldn't be a surprise to many field theorists. So that's the canonical example of a topological field theory. In this case, because there's no broken time reversal symmetry in the simplest case example, you get double Chern-Simons theories with U1 cross U1 gauge group in the simplest example in a way that you preserve time reversal. You can also talk about them in terms of discrete Z2 gauge theories, and so these topological field theories basically, as a rule, end up describing these gap states. Okay, and then one slide on quantum Hall effects. Basically, quantum Hall effects are more of the same, except you break time reversal. So you get ground state degeneracy in a torus, you get various entanglement entropies I didn't discuss. One new thing which is generic in quantum Hall states, but can also happen in the spin liquid states, you get gapless excitation on the edge, and these can also be understood in terms of the topological field theories. All right, so that's basically all I want to say about gapped quantum matter. These are non-trivial. These are states with non-trivial quantum entanglement, and our current understanding on them is based upon topological field theories, which are reasonably well understood, and we don't really need something dual to topological field theories to understand these sorts of states. I think that just makes life more complicated, I think. So I won't say any more about these gap states. So they just to get one category out of the way. Any questions so far?
How do you relate the gap edge states with topological gauge theory in the world?
Well, that's of course the classic result of Witten, I believe, where he showed that Chern-Simons theories with boundary had conformal theories on the edge. So that's similar ways.
Is a statement that any gap system can be mapped into some topological theory?
So far, that is the case. There may be some, non-trivial examples where people don't know how to do that. But as far as I know, in 2 dimensions for sure, every gap state so far has some dual topological field theory of this type. Yeah.
Is there some kind of like Heisenberg type model for these Mott insulators?
Yes. Yeah. So I could easily give a whole lecture on this, and I've spent many years of my life on these things. But yeah, so if you wanted to describe this RBB spin liquid, one way to do that is to write down an effective theory for these spins, and that's in terms of Heisenberg.
Can you make a spin chain for a particular dimension, direction, or?
Well, so I'm talking about 2D. So you can certainly make 1D spin chains, which are much better understood. In 2D, of course, now we have these wonderful solvable models of Kitev, which have given us, in some sense, confirmed a lot of these earlier understanding, but also given new examples of different types of topologically ordered phases. But those are rather special types of models where you tune things to make things solvable, but nevertheless, they've been very useful. A lot of this was understood, using various large N expansions and writing down effective gauge theories for low energy, guesses on effective gauge theories for low energy structure, and so on. Okay, so let's get to the meat of things then. So that's it. That's all I want to say about gap quantum matter. And so today's and perhaps even the next lecture will be on compressible quantum matter. I'm inverting the order now, mainly because, well, this is stuff of more interest and I want to get to it. And it's also where I think string-inspired methods will have a more fundamental impact, whereas for conformal quantum matter, it's sort of analogous to the quark-gluon plasma. You're understanding certain dynamical properties at finite temperature, but there's little doubt about even the basic structure of the ground state. Whereas in this case, even the ground state is not very well understood. Okay, so let me first begin. Oh, I should mention. Oh, yeah. So the new work that I'll talk about eventually today and also tomorrow is done in collaboration with Lisa House, who's a postdoc at Harvard, Max Mitlitsky, former student who's now at the KITP, and Brian Single, who's now a postdoc at Harvard. So let me actually spend a little bit of time on experiments, but at the outset, let me assure you I'm not going to explain any of these experiments. This is just as a way of motivation. So one of the well-studied class of iron high-temperature superconductors are these iron pnictides. So it's a messy crystal structure, but the important degrees of freedom reside on these iron atoms which live on a square lattice. And I won't write down any complicated Hamiltonian for them. But let me just show you this kind of picture of the phase diagram as a function of x. Here x is the relative concentration of phosphorus and arsenic. So it's something like pressure. You're just changing some parameter in the Hamiltonian, not changing the electron density in this case. And the vertical axis is temperature. And there's a variety of interesting phases. Of course, the most interesting feature of this phase diagram is that this critical temperature is on the order of 30 to 40 Kelvin, and in other related materials can be higher. So it's a high temperature superconductor. But what are some of the other features which are common to many of the high temperature superconductors? First of all, one is this region I call an antiferromagnet. In this case, it's also metal. And by the antiferromagnet, it means that the spins have some definite order. Half of the spins are up and the other half are down in some particular pattern that you can measure. And also it's a metal in this case, so these spins and the charge is also able to move around in some metallic manner. Now I won't say much about this again because this is a state that in some sense you can understand quite well by adiabatic continuity to some particular one electron state. You take a state where you have different orbitals filled for spin up and spin down in a way that you get the spatial modulation, and from that one electron state you can understand this metallic antiferromagnet, at least its basic properties. Okay. Then you have the superconductor, and I've already given you a theory of superconductivity, electrons, pairs, and Bose-Condensed. All right. And then out here is an ordinary metal. So the color plot here is to represent the temperature dependent of the resistivity. It goes as T to the power alpha, and here alpha has the power 2. So let me just quickly review then what is our theory of the ordinary metal, going a bit beyond the one electron picture.
Can I ask a quick question?
Yes.
Superconductor is D wave?
Well, it's most likely what's called S plus minus, but that's basically the moral equivalent of D wave, but because the Fermi surface geometry is slightly different. So the hallmark of D wave is that you have Cooper pairs that have different signs on different portions of the Brillouin zone. And in the cuprates, they have a D wave signature. So the Cooper pair on a D wave state. Now, so what's special about the D wave for the cuprates? So one interpretation is that the two electrons in a Cooper pair can get scattered by momentum pi pi, which is the momentum carried by the antiferromagnetic structure, which is the momentum of the wave vector of that structure. And when you scatter by that momentum pi pi, you should pick up a minus sign. Now, the lattice geometry in this case is somewhat different, and so is the antiferromagnetic wave vector. In this case, is pi 0 and not 0 pi. But if you do the analogous process where you scatter a Cooper pair by the antiferromagnetic wave vector, you should pick up a minus sign. If you look at the analogous state, it turns out to be not D wave in this lattice. It's something called S plus minus, but okay. That would be all right. Yeah, I think it's not fully settled, I should say, but that's the weight of the evidence so far. And it's pretty convincing.
Can I ask another question?
Yeah.
You said increasing X doesn't change the density of charge carriers.
In this particular system, that's why it's a beautiful system, because arsenic and phosphorus are isovalent. So you remember little chemistry. Arsenic and phosphorus are the group 5. So if substituting arsenic for phosphorus doesn't change the number of electrons. So this is it's a pretty unique system in that regard, that you're able to scan out the whole phase diagram by keeping the density fixed. That makes it a much nicer system to study because it's much cleaner and doesn't have all kinds of puddles of charge floating around and so on, and long-range interactions from the ionic impurities. So, and that may be one reason why the phase diagram is so beautiful, to me anyway. Okay. So let me just review what is an ordinary metal. So as I said, an ordinary metal, now in a different view, this is a Brillouin zone, and you draw some band structure, which is a dispersion for the electrons, and you fill the low energy states. So for the cuprates, the band structure happens to have the peculiar feature that the low energy states are outside rather than inside, but that's nothing mysterious. It's easy to understand that for certain lattice structures. So the occupied states are here and the empty states are here, and that's the one electron picture. The most important property of this one electron picture is what's called a Fermi surface, this line here, which separates the occupied states from the empty states. Now in the one electron picture, you would also conclude that the area enclosed by the Fermi surface, let's think in terms of holes. Okay, so there's some density of holes in the system. So the area enclosed by the Fermi surface should equal the density of holes, or the density of, So that's a natural feature of the one electron property of system. And what's been proven in Landau's Fermi liquid theory, that feature holds no matter how strong the interaction, as long as you're adiabatically connected to this one electron state. So the key features of the Fermi liquid is that first of all, the Fermi surface is preserved, even though it seems like a one electron concept, but it isn't. You have to define a bit more carefully, but there's a closed analog of the Fermi surface that's preserved. And the area enclosed by the Fermi surface is equal to the electron density Q. So this is sometimes called the Luttinger theorem. It's not really a theorem, but it's really a statement of adiabatic continuity that as long as you're in this Fermi liquid state, then by definition, the area enclosed by the Fermi surface will equal the charge, the electron density, or the hole density, which I'm going to call Q. Okay, this is going to play a very important role even in holographic descriptions. You have to keep track of where the charge is and how that's related to low energy excitation. So one feature of the Fermi surface I've already mentioned is that's where all the low energy excitations are. When you excite the electrons, you move an electron from here to here. And if you want to think in terms of single electron excitations, it's very useful to imagine that this is the line of zero energy excitations. So there are electron and hole excitations, both of whose energies vanish along this line. So unlike a massless Dirac particle, whose energy only vanishes at k equals 0, here you have some excitations, both electrons and holes, which vanish on a line. And that line really has to be there to all orders of interaction. And furthermore, the area enclosed by the line must equal the charge density. So these are, very beautiful results of Landau's Fermi liquid theory, very robust results which have been confirmed in many, many experiments. Okay. And they're really quite deep, and there are analogs of these results we believe should also apply to other compressible or metallic states. Okay, among the other properties that emerge is if you look at these zero energy excitations along this line in Landau's Fermi liquid theory, then you need something to absorb the momentum and if you take some reasonable assumption on what leads to momentum relaxation, you get a resistivity that goes to T squared. Okay. All right, so and here indeed you find T squared. So the elephant in the room then is this big red region in the middle, which for want of a better word I just call strange metal. So one of its properties here is that resistance is linear in T. Doesn't go as T squared. But many other properties are quote unquote strange. If you did measurement of the one electron Green's function by photo emission experiments, or looked at optical conductivity, or looked at NMR relaxation, various properties would be different with different power laws from that of a Fermi liquid. And so what we need are theories of such strange metals. Now, in this particular system, it seems very suggestive that this strange metal really has something to do with this antiferromagnetism disappearing and this superconductivity here. And these are very specific, detailed properties of this material. So that's the reason I said I don't think string theory is anywhere close to talking about such strange metals. But this is a very beautiful experimental example of a strange metal, and we want to understand strange metals however they appear. We have very, very few theories, and in fact I'm going to list all of them today, of strange metals. and even those are incomplete. Yes?
Does it mean that whenever you have a strange metal, if you go make it very, very cold, you'll always end up with superconductivity?
Okay. It's experimentally that seems to be the case, yes. Theoretically, is that always the case? I think the answer is no, and there's a paper coming out on that question soon. But okay, but in most cases, yes, I think the answer is, and I suspect also in many string-inspired examples that may be the case. But all right, we'll see. But that's an interesting and important question, certainly. Yeah.
You said the optical conductivity is anomalous. Do you remember the fall-off in this?
Oh, yes. I don't know if it's measured in this material. Yeah, I'm sure they could do it. So this is a relatively new material that's just been characterized. I don't know off the top of my head if it's been measured. Yeah.
I don't know if you want to elaborate, but don't you have this notion that at zero temperature you have to have zero entropy, and therefore fermions should somehow form bosons to do that?
No. I mean, the Fermi liquid has zero entropy at zero temperature. There's no problem with entropy. It obeys the third law of thermodynamics. It's just the excitations, there are lots of low energy excitation. So the specific heat vanishes at zero temperature, but vanishes rather slowly. And we are going to look for strange metals. In all experimental examples, the specific heat vanishes even slower. So in some sense, strange metals have more excitation at low energy, but they all entropy is zero, as far as I know. Certainly in the Fermi liquid and all the examples I discussed, the entropy at zero temperature is zero. There's no violation of the third law of thermodynamics. Now, but the question is this state always unstable? So there's something called the Cohn-Luttinger instability, that there's always some high angular momentum channel in which you get some attractive interactions. So under a wide class of conditions, that's true, but it's possible to find conditions in which that instability is not present. Particularly if you break time reversal, or if you get a strange metal under certain conditions, it doesn't seem to be there. So we're just going to treat this essentially as a stable state. Although eventually at some exponentially low temperature, there may be some pairing instability. But that's actually a very important, both of you raise a very important question. What is it that suppresses the pairing scale relative to the scale over which you see strange metal physics? In the very simplest analysis, you often find they're about the same. But experimentally, it seems to be that there's a clear distinction. And that's something that perhaps holographic methods will lead to some insight on. Okay. And so this is the other high temperature superconductor. It has a more complicated phase diagram, been studied much more carefully over the years. So I'll just mention one important difference in this high temperature superconductor. It's not as clear that the antiferromagnetism plays such an important role because it's at much lower doping. But there is then a strange metal here also with many similar properties to those of the other example. Okay, so that's the end of my solid state introduction. So let me now define, let's turn into theorists and let's look at a manageable problem. This will be difficult enough as far as I'm concerned. So let me first define what I mean for the purpose of this lecture by compressible quantum matter. Just a very simple definition. Take any infinite continuum translation invariant quantum system, and the only thing I want from you is a global U1 charge, which I'll call Q. This is, of course, the proxy for the electron density in most cases. And I'm going to be in spatial dimension d greater than 1. Actually, you could equally well be in d equals 1, but as you'll see in a minute, that d equals 1 is special for many reasons. So the interesting and difficult problems on d greater than 1. Okay. Then all I ask is write down a zero temperature phase where dq d mu is non-zero. In this case, mu is the chemical potential, which means I just take my Hamiltonian of the system and just shift it by minus mu q. That's all. So that's the compressibility dq d mu. As you change the chemical potential, the charge q keeps changing. That's it. Okay. So this is any phase that satisfies these two conditions is an example of compressible quantum matter. And what I want to do is write down the list of all ground states that obey this. Okay. The list is extremely short. The only state that we understand very well that obeys these two requirements is the Fermi liquid, and that's the end of the list. So why is it so difficult? Oh, sorry, I'm being a little bit. There's one more condition. There are other states. I don't want to break either any of these symmetries. So I don't want to break translation invariance, and I don't want to break this global U1 symmetry. It should remain unbroken. Okay, sorry. So why is this difficult? So first of all, just this definition, you should easily see that any such state that's compressible must be gapless. So if you have some set of eigenstates with some energies, that's the eigenstates of Hamiltonian H. Then I just add this term. Now Q commutes with H because it's a conserved charge. So adding this term is not going to change the eigenstates. The wave function will still be eigenstates of this modified Hamiltonian. So the eigenenergies are going to move. So as you add some mu, so this might go up and that might go down and so on as a function of mu. So these energy levels start moving. But if you're sitting here and the other state is a finite distance away, the ground state wave function is not changing. So if the ground state wave function is not changing, well, q is not changing as a function of mu, and so dq dmu is 0. So the only way you could have dq dmu non-zero is if there was actually a whole continuum of states right above your ground states. And as you attain the chemical potential, the ground state, the states exchange positions. Some other state became the ground state. Only then could dq dmu non-zero. So you have to have a gapless system. So how do you ensure that there's no gap? Well, one way to ensure it is by breaking a symmetry. We know Goldstone's theorem. So you have two continuous symmetries here. One is translational, the other is U1. You can break either. If you break translational symmetry, you get what we call a solid or a charge density wave. And in a solids are compressible, well, you can just compress a solid. The atoms or the electrons move closer to each other. It's compressible. So that's fine. If you break U1, you get a superconductor or Bose condensate. And those are compressible because you can always add particles into the Bose condensate without any trouble, and so they're compressible. So you want to have many gapless excitations, and to have a non-zero compressibility. Okay. All right, so let's take another example of a gapless system. Let's take a massless fermion. So let's take a massless Dirac fermion. So this in momentum space has a 0 here. So this is K and this is E. Okay. So this is a gapless system, but is it compressible? Well, let's see. If I change the chemical potential a little bit, I'm going to occupy states over here. So how many states have I occupied? So if I, let's see. So this is energy, so that's the chemical potential. So basically the charge Q is, I integrate from 0 to mu of all the states from here to there. So that will be K to the D minus 1 dk. So that you see goes as mu to the d, and so dq dmu goes as mu to the d minus 1, and so in d equals 2 at mu equals 0, which was the original point, this is 0. So this goes to 0 for d greater than 1. So in fact, just having a point of at which you have gapless excitation, not enough in dimensions d greater than 1. In one dimension, it's fine. So 1D, a relativistic system, is also compressible. So in my classification, where I divided quantum matter into gapped, conformal, and compressible, in 1D, conformal and compressible are really the same thing. In higher dimensions, they're not. So in higher dimension, to get something compressible, it's not enough to have gapless excitation at one point. In fact, you need gapless excitation on a surface of codimension 1. So in 2 dimensions, you need gapless excitation on the whole line. In 3 dimensions, you need gapless excitation on the whole surface. So these are the states that we want to understand. States with 0 entropy, but with lots and lots of gapless excitations, much more than you're used to in particle physics. So this I've already said. The only compressible phase of traditional condensed matter physics is one which does not break the translation U1 symmetry, is the Landau Fermi liquid. In any, there are many variations on this theme, but I don't know of any other example which somehow cannot be mapped onto this state. Notice I didn't say anywhere that your system should have bosons or fermions. It could be a system of anything. But ultimately, getting a line of 0 energy excitations is natural only for fermionic systems. So that's why compressible states of this type are usually in fermionic systems. Okay. So then, here's my challenge to string theory. It's very simple. Classify and understand non-Fermi liquid phases of compressible quantum matter. I don't care, since our list is so short, I don't care what your Hamiltonian is. Give me another example on this list. There's only one, okay? And this is my definition, if you wish, of a strange metal. A strange metal is any metal which is compressible, which is not a Fermi liquid. Okay, that's, I think, a reasonable definition. It's very broad. I'm not trying to explain barium, whatever it was. Barium, potassium, iron, phosphorus, nothing. I just want any Hamiltonian which has a compressible ground state. Okay? And in fact, even I'm going to be happy, raised some of the questions that arose. It may well be that many examples of strange metals you cook up eventually are unstable to something else, to a superconductor or a solid, charge density wave. Fine. I'm happy with that. Even I'm happy to admit that metal into the family of strange metals. But I want to understand, why is that instability scale so low, or what is that instability scale? That's really the key question. Where is that instability scale? That will tell us where is TC. So if you view the big problem is understanding why is TC so high in the high temperature superconductors, or what is TC? Can you predict TC for the high temperature superconductors? If I had a quarter for every time people ask me that, I'd be wealthy. Well, we can't. But I think the route that this suggests is that really the first thing you got to do is understand the strange metal, and then the next step will be understanding with possible instabilities, and that seems to be a prerequisite for understanding, determining what TC is. So we're a long way from that. Okay, so I'm going to then give you today, how am I doing on time? Okay, I'm about halfway through today, is that right? Give you one example of what we believe, we're pretty confident in condensed matter is a strange metal. I'll write down its field theory and do a few calculations. But even in this example, we run up against some difficulties, which I'll try to describe. And then we'll turn to a lot of guesswork on how holography might shed some light on this example of a strange metal. Anyway, so it's a good time to pause for questions. Any questions so far? This is all introduction, motivation so far. Anyway, I haven't done any calculation. Yeah?
This might be a stupid question. I don't know much about superconductors, but you said they're gapless, but often, is the essential physics of superconductivity is in the gap.
Okay, so a superconductor, like a BCS superconductor, has two sectors in its Hilbert space. The fermionic excitations, where you eject a particle from a superconductor. That fermionic sector has a gap. But there's also a bosonic sector, which if you wish, is just at least a neutral superfluid. The Cooper pair is moving around. The phase of the superconductor, that's gapless. Now, because of the long-range Coulomb interaction, there's some caveats to that statement, but okay, we'll ignore that. But you can twist the phase of a superconductor without costing any energy. As long as it's static, that's correct, even with long-range interactions. That's the gapless sector. So you have to, So here I was talking about the full sector. So the superconductor in that sense is always gapless because it's got this bosonic mode that's both condensed. But the fermionic spectrum could be gapped or not, depending on what kind of superconductor you're looking at.
Why do you exactly want to approach the superconductor phase from the strange metal direction? I mean, why? What about approaching it from other phases?
That's the story of my last 20 years of my life, is trying to approach it from the other direction. So I'm trying something new. No, people have tried that, of course, and with varying degrees of success. And none of those approaches explain the strange metal. So let's try something else. Yeah.
So in the experiments, do the strange metals obey Luttinger's theorem?
Excellent question. Yes, in fact, on the cuprates, if you look at the Fermi surface, it does seem to be consistent with Luttinger's theorem. Yes. I'm going to turn to that precise question shortly. Other questions? Okay. All right, so let's actually write down a field theory for what might be a strange metal. Okay, so I come back, this is part of my reason for introducing gap quantum matter. I come back again to this example of this R resonating valence bond spin liquid. So another model which has gained some support in recent years for the spin liquid is not this gap Z2 spin liquid that I talked about, described by topological field theory, but another type of spin liquid which is often called a Bose metal or a U1 spin liquid, in which you have these fermions. These are basically the remnants of the electrons, sometimes called the spin-ons, interacting with an emergent gauge field. And for simplicity, I've just written that as a U1 gauge field. So here's the problem. I mean, so this is the field theory that I want to think about. I have fermions in a finite chemical potential. So there's initially a Fermi surface, and then I just couple them to a gauge field. That's it. Now, exactly how this model arises from a spin liquid will take me a little far afield. I'm not sure I want to go that route. I mean, I can just postulate it. But just to give you some idea, so these fermions are the spin degrees of freedom on each side. And the gauge field, the flux of the gauge field, is really is an operator that causes resonance. So there's you take this operator, like think of a benzene molecule. So you have these resonance states of a benzene molecule. Okay, and so you have think of this as this valence bond here. So now on this hexagon, if you want to act an operator that takes you from this state to that state, that operator you can actually interpret as the flux of a gauge field acting on the fermions sitting on these sides. So there's a long story how that was all well understood, but that's basically the idea. Now, what's different about this picture of the spin liquid and the other one I presented is that we are assuming that these fermions are actually forming a Fermi surface initially anyway. And that Fermi surface is stable to adding on a gauge field. And in fact, we can check that at least locally stable. Now, we don't know whether for the Hubbard model is a good starting point, related to David's question. We certainly don't know that. That's a conjecture. But for this purposes this talk, let's just take this as a Lagrangian we want to understand. Okay. Now, you might say, wait a minute, copper also is described by this Lagrangian. Electrons in copper are coupled to U1 gauge field, which is ordinary electromagnetism. So how come why isn't copper as strange, something mysterious? Well, the difference is that in copper, there's another term here, which is F mu nu squared over 2 E squared. And in copper, if this was ordinary electromagnetism, E squared is practically 0. It's 1 over 137. And because of that, all the effects I'm going to now discuss are suppressed to ridiculously low temperatures. So whereas ordinary electromagnetism might destabilize copper or more probably any two-dimensional metal, those effects are completely negligible. So what's important about this particular emergent gauge field, it's not electromagnetism, it's associated with the flux operator that causes resonance. What's important about it is that E squared is of order 1. Or even better, it's infinity. It doesn't really matter. You're in some strong coupling phase where E squared is of order 1. And so you really have to think about dynamical fluctuation of the gauge field much more carefully.
This is a 2 plus 1 dimension.
Correct, yeah. That would be the most interesting case, of course. Or a more physical way to say it is, electrons in copper have Coulomb interaction, which is instantaneous. But as the electrons are moving, they also radiate photons, which the other electrons will interact with. But those effects are, spin orbit effects, they're just negligible. Here, these radiating photon effects are much, much stronger. They have order 1 or even, so you can't ignore them at all. All right, so this in some sense is a very old problem. This Fermi surface coupled to a gauge field, but it's still a problem of some set. So this is one problem, one strange metal I'm going to now say more about.
So are you also going to include a Lagrangian for the gauge field?
It's your choice. It doesn't really matter in the end. So you can take E squared to infinity if you want. you could just work with this. You're going to work at infinite gauge coupling if you want. But even if you have a finite gauge coupling, it won't affect things. We believe that if you always flow to the infinite gauge coupling, strong coupling limit. If you feel better, I'll put it up there, but I can't change my slide. We'll see in a minute why we won't need it. Yeah.
You said that for copper went away,
Yeah.
but for this one it was relevant because it was of the order of 1. So
Well, so strictly speaking, for copper, it's also important. But just to see it's important, you have to go to very, very low temperatures. And before you get to such temperature, other things happen, superconductivity being one of them. So it's never, I don't think the effect's ever been measured in real metals for ordinary electromagnetism. Now, if ordinary electromagnetism if alpha wasn't so small, you could see it in copper too. We would have understood this problem a long time ago. But maybe it would have led to problems with the Sommerfeld block theory and we'd get nowhere. All right, so I guess I'm showing one more slide. So there's another problem. This is maybe for the well, okay, let me just quickly go through it. It's not really necessary for the things I'm going to say. There's another problem, so-called nematic transition, which is seen in these experiments at this temperature. Okay, I won't go through it. But what is this transition? So imagine a system where you have some Fermi surface, which has a square symmetry of the square lattice, as you do in the cuprates. And then for some reason, this square-like Fermi surface wants to become rectangular. So there's some interactions, and for some reason it wants to break symmetry and become rectangular. So I associate this rectangular shape with an order parameter, an Ising order parameter phi, which is positive. And so then the other rectangular shape would have phi, which is negative. So this symmetry is called the Ising nematic symmetry, just basically symmetry of reflections about this axis, which is preserved. And so the question is, suppose a Fermi liquid, for whatever reason, as you've tuned some parameter, decided to go from square to rectangular. This is just like a magnet. As you lower the temperature, it decides to go from paramagnet to all spins up or down. Here the analog of up or down, or rectangular vertical or rectangular horizontal. So then there's some coupling R, and then a critical point, quantum critical point, where you go from square Fermi surface to rectangular Fermi surface. And it turns out that at finite temperature is a lot of good theoretical evidence and perhaps experimental evidence that here you also get a strange metal. And curiously, the theory of this strange metal is almost the same of the Fermi surface coupled to a gauge field. So in one fell swoop, you'll also solve this problem. Okay, this is just further motivation. So let me just go back to the original problem. Okay, we start with free electrons with some short-range interactions that I won't bother to write down, which form a Fermi surface. And as I said, the area enclosed by the Fermi surface is equal to determined by the chemical potential, but more precisely, it's equal to the charge density. And what I'm going to do is just add a fluctuating gauge field. Okay, so now I'm going to summarize what we believe are the properties of this system. And then by the end of today's lecture, I'll derive some of them. Yes?
So you're actually saying it's a fluctuating gauge field,
Yes.
but you told me the coupling is very large or something, so
Yeah.
why would it be fluctuating? Wouldn't that be
Well, I
suppressed
think
if
it's the other way around. If this coupling goes to 0, then the fluctuation is suppressed.
Okay,
If the coupling goes to infinity, the fluctuations are not controlled at all.
I see.
The coupling is 1 over e squared. Okay. All right, so let me now summarize what we know about what condensed matter physicists with varying degrees of confidence believe they know about this system. So that's it. It's just fermions in a finite chemical potential coupled to a gauge field. All right. So what are some of the things we know? Well, first of all, we believe that there is a sharp Fermi surface. And how is the Fermi surface defined? It's defined as the zero of the inverse Green's function. So you compute the inverse Green's function as a function of momentum and frequency. Then you put omega equals 0, and then you find that at some finite k, as k equals kf, G inverse has a 0. Now this, if you just took a free electron problem and compute, wrote down the Green's function for free electrons, which is extremely simple. For free electron, it's omega G minus k squared over 2m minus mu. You surely find this is the case. You put omega equals 0 and k squared over 2m equals the Fermi energy, then G inverse is 0. Now in this case, there's one little twist which is actually crucial, and this is where horizons and black holes and stuff will come in. This Green's function is not a physically measurable quantity because it's gauge dependent, at least for this gauge problem. So I'll refer to this such Green's functions as requiring hidden Fermi surfaces because there's no Green's function. Yes?
Is it clear that the Fermi surface doesn't show up in the gauge invariant quantity where you run a Wilson line between the fermion insertions?
It may, but okay. But I think so. There could be other observables in which the Fermi surface shows up, but I don't believe there's any other observable which gives you any observable that will give you, exactly kf at exactly these locations. Because in fact, I know I can move this Fermi surface around by gauge transformation. So the position of it is not even gauge invariant. But in any given gauge choice, we believe that there is such a Fermi surface. Okay. So these are difficult and important and key questions. So anyway, okay. So I'm going to derive some of this hopefully by the end of today's lecture. Let me just write down the conclusions. So there is a Fermi surface given by the 0 of the Green's function. Now in a Fermi liquid, however, that's next slide. We know what happens near this point too. Okay. Number 2, the area enclosed by the Fermi surface is exactly that in a Fermi liquid. It's equal to the fermion density. Okay, and then number 3 is the new thing now. That near this Fermi surface, you have lots of excitations at low energy, but these disperse as omega as q to the z, whereas z is a dynamic critical exponent. Sorry, there should have been, I screwed up my slides. Q is the distance from the Fermi surface, right over there. So again, let's look at the case of the Fermi liquid. So here's my Fermi surface. So G inverse is equal to omega minus, so this you can expand about the Fermi point is omega f Vf times k minus kf. So this is modulus of k. This is what I call Q. So in a Fermi liquid, omega goes as Vfq. So there are low energy excitations. On one side they're particle-like, on the other side they're hole-like. Just like in a free Dirac fermion, I guess. And they disperse in this strange way away from this line of zeros. Omega going as q. So in this sense, this exponent z is 1. Now in a non-Fermi liquid, in general, the states that we find are dispersed with some anomalous exponent z. So this is the first example of a critical exponent. This is, determining what z is an important goal of the theory. And typically we'll find that z is greater than 1, meaning that as q goes to 0, there's many more low energy excitations. So things are becoming worse. They have many more low energy excitations. So, it's better depending on perspective. It's a stranger state. And even a Fermi liquid, when you think about it from field theory perspective, is a very strange state. This is even stranger. Okay.
Do you know what z is in this example?
Yes. Well, I'll come into that. That's in fact the next point. Okay. So there have been various computations, and I'll just in some 1 over n expansion that I'm going to describe. And what we know is that this spectrum of this inverse of the Green's function near the 0, so there's q. So as I approach Q and look at the excitations here, this hazy stuff. The haziness is supposed to remind you of lots of low energy excitations, but they're very blurry because they're not particle-like. So that's my picture of a strange metal with a hidden Fermi surface at a very precise point and lots of blurry excitations around it. Okay, so near this point, this Green's function obeys this sort of scaling form. It's some function of omega to the q over z. And so in the Fermi liquid also we can write down Green's function this way. So this I can write down as full order factor of q times omega over q minus Vf. So this is my function f, and that's q, and so eta is equal to 0. So what we notice here in the Fermi liquid that this scaling form is purely real. Okay, this is simply saying the particles live forever. There's no damping. Now, if you do a more careful study, as you do in Landau Fermi liquid theory, you find that there is a term here, I omega squared. So if you put that, so that I omega squared gives you a damping. Well, this is a correction to scaling. So it's very weak. It's not part of this leading scaling bit. So it depends on formally and some irrelevant operators. That's one way to think about it. And in that sense, in that sense, the Landau Fermi liquid is just a theory of infinitely long-lived particles near the Fermi surface. It's essentially a free electron theory. Now, in this case, in all the computations we have, f is a complex function. It has a pole or branch cuts of order 1, and so there's no reason these excitations are not well defined at all. There's there's always an imaginary part which is as large as the real part for most generic cases. And I think John will give us examples of holographic solutions of these type of things which also share these features. Although in John, at least the cases I think John will discuss, those are gauge independent Green's function of slightly different type, which I will try to motivate a bit later. These are gauge dependent. Okay, and so the 3-loop computations so far show actually z is 3/2, possibly with corrections, but no one's ever found any. Okay, and I'm going to derive the 3/2 in a minute. Okay. Yes.
Can I ask a question? In some earlier literature along these type, in this same system, I remember some I omega to the 2/3.
Yeah, that's related to this.
Is that 3/2 the same as the 2/3?
Yes. I'm going to derive it. So the final thing is to look at the entropy of the specific heat. So if you work out the entropy of this theory, it turns out to be T to the D effective over Z, with D effective equals 1. So why have I written it down this way? Well, this entropy going as T to the D over Z is just the Stefan-Boltzmann law. So remember, what is the Stefan-Boltzmann law? Stefan-Boltzmann law is Stefan and Boltzmann were considering a black body. The modern interpretation of a black body is photons in thermal equilibrium. So we have photons in thermal equilibrium. That's dimension d equals 3, and omega equals ck. That's the dispersion of photons. And the entropy goes as T cubed. Okay. Now, if you did the Stefan-Boltzmann law in any dimension, omega equals ck, you will find without any trouble, it's an undergraduate problem, because it's T to the D. Okay, if you extended that to make D, omega going as K to the Z for free particles, that goes as T to the D over Z. It's the same integral, just do the same calculation, d dk n of omega equals K to the Z, you'll get T to the D over Z. So this property, the entropy goes as a dimension of space divided by Z, is of course natural for systems whose energy vanishes at a given point in momentum space. Okay, and then for a critical theory, this it still goes as T to the D over C, and this property is sometimes called hyperscaling. Okay, hyperscaling is a buzzword that condensed matter physicists love to use, but it's just simply the statement that the free energy of a bunch of stuff at temperature T goes as T, or the entropy theory, T to the D over Z. Or another way to say it, it's simply the statement that the canonical dimension of, the scaling dimension of the free energy is just its canonical dimension. Okay, so it's the statement the stress energy tensor has dimension 1 over 2D. So these are all equivalent statements that energies and entropies all scale with the naive scaling dimension. That's called hyperscaling in condensed matter physics. So what we see is this state clearly violates this law. It goes as 1 over Z. But again, you can understand this because the difference between this state and the Stepan-Boltzmann law, there you have zero energy excitation, 1 point in momentum space. Here you have zero energy excitation on one line, and they only disperse in one direction, transverse to that line. So because they disperse only in one direction, you expect the entropy to go as T to the 1 over Z. So they behave like a 1D system, at least as far as counting phase space of low energy excitation is concerned. This is not to say it's a 1D field theory. It's just that the phase space of independent low energy excitations is one-dimensional. Okay. All right, so those were 5. I see I have a very ambitious plan. So those are 5 statements of this strange metal. And of course, I've set it up because all of these statements are realized in varying degrees, both in field theories and also by holography. And this is my aim to show you over the next 2 lectures, or this lecture and the next one, how that happens. Yes?
Is the prefactor of the T to the D to the 1 over Z understood?
It's not. It's surely non-universal. It's not dependent. Not a universal quantity. Well, I mean, okay, because Z is anomalous, so there might be some ratios with other things.
It's not the area of the Fermi zone? It's not
No. For the entanglement entropy, the prefactor is I'll come into that. But I haven't been discussing. But for the thermal entropy, the prefactor is not universal. And again, you see that from holography also.
Question?
Yeah.
In the three-loop computation, is perturbation assumed?
Yes, it's assumed. So that's why I'm not declaring the problem solved. A lot of things are assumed. Okay, so let's do a computation. Yes.
I just want to understand so what is the gauge independent statement? I mean, the eta and Z are gauge independent, presumably.
Oh, good question. So eta is gauge dependent, but Z is gauge independent. You can view this as the definition of Z, which is a gauge independent definition.
But eta depends on the change.
Yes. Now there's a very natural gauge in this case, which is Landau gauge. And the reason it's natural is because that's precisely the observable gauge for the Ising nematic problem. And also the calculation, as you'll see, much simpler in that gauge. So there's a very natural gauge for which everyone could use eta. But even for the example of a Dirac fermions coupled to gauge field, the eta is gauge dependent there. Okay, let's do a computation. And actually, I have slides on this, but so here's the problem. So the problem we're looking at, let's go back. Here's the problem. There's the Lagrangian, and I'm going to do 1 over NF expansion. NF is the number of flavors of fermions. Okay, sigma will go from 1 to NF. So it's called a vector large N limit. That's the large N limit we're going to take. It's the old-fashioned large N limit, and which has kept condensed matter physicists happy for 20 plus years. So why are we not happy with it? Well, you'll see in a minute. Okay, but let's just go ahead and do it. Sometimes the condensed matter is called RPA, or there's 20 years of work on doing this kind of perturbative expansion, and I'm just going to summarize some basic properties. Okay, so here's one, actually the most simplest way to do the calculation. So we agree. So what's happening here? So the electrons, there are lots of electrons near the Fermi surface, and they emit gauge boson and they absorb gauge bosons. Okay, so the electrons are moving around, radiating gauge bosons and interacting with each other. Okay, so now the electrons, of course, have a very hard time scattering here because of the Fermi surface. It means there are lots of states that are prohibited to them. That's the key thing about a Fermi surface. It excludes states for the electrons. So electron going back, sitting at this point in the Fermi surface, it wants to emit a very low energy photon. Well, the most efficient way it can emit a low energy photon is to scatter tangentially to the Fermi surface. Because the energy, so if it emits a photon of momentum q, its energy will change as only q squared if it goes tangent. If it goes if you go orthogonal to the Fermi surface, energy will go as q. So the most low energy photons are emitted if the electron gets scattered tangent to the Fermi surface. Okay, so this means that if I take an electron here, it's going to scatter off a photon most efficiently where the photon q points in this direction. All right. So let's assume that most important photons are in that direction. Now the photon is a transverse gauge field, or in other words, if I pick Landau gauge, and this answers one of Andre's questions. So the photon is moving this direction. So which is the photon that has momentum q in that direction? Well, since the photon is transverse, it's a sub x. So the component of the photon along this direction is the one that's going to have the physical photon have momentum in that direction. So we're going to expand the fermion kinetic energy about this point. So for the fermion, its energy in this direction goes as x, kx, and the energy in this direction goes as ky squared, because it's tangent to the Fermi surface. And then I already said this, sorry, the other way around. And under gauge, only need the component of the gauge field orthogonal to q. So there's just a scalar. The photon effectively becomes a scalar in 2 dimensions. This is in 2, which you already know. The photon is just equivalent to a scalar. In this case, we choose our scalar very carefully. We choose our scalar to be always associated with the momenta. So if I'm talking about this point of the Fermi surface, our scalar is the component of the gauge field orthogonal to this direction, parallel to the Fermi surface. So that's has to be defined very carefully around the Fermi surface. That's the scalar. Okay, if you're doing, you know about the duality between electromagnetism and scalars in 2+1 dimensions. That's all done at 0 momentum, but here I have to do a little more carefully at these points around the Fermi surface. Okay, so in the end, what do I have? I have 2 fermions. I have this fermion psi plus sitting at this point. And it turns out you also have to account for the fermion psi minus sitting at the antipolar point, because that's the only set of fermions that have the same tangent. So if I pick this direction q, then the photon in this direction will couple most efficiently to fermions here and fermions there and nowhere else. Everywhere else, the energy of the fermion will go linearly with q. Here it goes quadratically, and there it goes quadratically. So you just pick out those 2 points. Okay, so now I can write down a field theory. That's the field theory. It's an innocent looking field theory, but it's the cause of all our troubles. So the field theory is a field theory of 2 fermions, psi plus and minus, psi plus sitting here and psi minus sitting there. So psi plus has a linear dispersion in the x direction and a quadratic dispersion in the y direction. So d by dx, d by dy squared. Psi minus also has a linear dispersion in the x direction and a quadratic dispersion in the y direction, but the dispersion in the x direction has the opposite sign. It's a chiral fermion. So this is the right moving fermion, that's the left moving fermion in the x direction. If I throw out the d by dy squared, that's exactly your C equals 1 conformal field theory with a left moving and a right moving fermion. So that's the right moving fermion, that's the left moving fermion. But there is also a y. Okay? So there are 2 chiral fermions which have some of the chiral structure, but they also have this curvature correction. Okay, now the coupling of the chiral fermion to the gauge field is exactly again as in CFTs, TFT2s. It's just, this is the current, psi dagger left, psi left, minus psi dagger right, psi right is the current, couples to the gauge field. Done. Okay. So if I just threw out the d by dy squared terms, that's the Schwinger model in 1+1 dimension, which we know as a massive phase, as chiral symmetry breaking and whatnot. So all of the complications are the d by dy squared. Now, you'll be happier now. Here's the photon term, 1 over g squared d by a squared. Okay, I put it in there. Okay, there's also, I should also put in a d by d tau a squared, but neither of those really matter. And g is the gauge coupling constant. I'm calling it g. Sorry, I call it e. Okay, on g. So that's your homework problem. Solve this field theory. Well, that's what I told Max, and he made a lot of progress. So sometimes you get lucky. Yeah.
Right. Is that not throwing out information about the topology of the Condensed surface?
We're just focusing on these points because the others decouple from each other. So what happens in the end is that the photons in different directions basically factorize. So the system factorizes into an infinite set of these chiral field theories. Again, this is all perturbative, assuming this is what happens. We don't really know that. But to all orders in 1 over nf, so you give these fermions now some additional flavor index, we believe that can be established. These are the terms that give you the most singular infrared divergences. Okay. So, as I said, if these were Dirac fermions, then this is again something that the 1 over nf expansion can solve. It gives you CFTs that are well understood, somewhat analogous to M theory. We think we know a lot about the system, but this is not Dirac fermions. These are not 1 plus 1 dimensional, but they have some chiral character, and they also have this crazy d by dy squared, and this seems to lead to all kinds of problems. And so this is one of the proposed field theories then of a strange metal. Yeah.
So that's a field theory at the fixed point.
Yes. So now for the gauge field, it's believed that there's actually a whole phase. You can vary anything you want. It's always going to flow to this low energy limit.
If you move your points around your
Yes.
square,
Yeah.
x and y directions change.
Correct. Yeah. So you have a whole infinite set of such theories, but they all have the same structure.
Can you relate them?
Yes, you can. Okay, but I'd rather not go into it. So there is a kind of a sliding symmetry where you can slide from one theory to the other, which ensures that you're not overcounting the degrees of freedom. So this theory has a certain symmetry, which is sort of like Galilean transformation between the x and y direction, and that's like a rotational symmetry, which actually ensures that the entropy goes as t to the 1 over z, not t to the d plus z over z or whatever. It's really, as far as degrees of freedom is concerned, because there's a additional symmetry here, it's like one-dimensional in terms of counting an entropy. Okay. Really, so at this point, here's the field theory. I hope I have motivated it. You can now open Peskin and Schroeder and evaluate thousands of graphs, or Mahan or Abrikosov, Gorkov, Zaloshinsky. You apply those methods and you evaluate thousands of graphs, and people over the last 20 years have done that, and I'm going to evaluate 2 of them right now that give you the basic ideas. Okay, but any more questions on where this field theory came from? So it's our attempt, our best attempt so far, to write down something for which we understand the most. There are other possibilities, something that's not generically an Arnold Fermi liquid, and it's a compressible state which, under suitable conditions, in this case we also believe can be stable down to 0 temperature. Okay, maybe I made a strong statement there, but I think that's fine. Under suitable conditions.
I'm worrying about the global effects. So there are some quantities which depend on the global structure of the Fermi surface, right? Which
Yes.
in the patch theory you get infinity for.
Like which one?
If you can beat the density, for example.
Yeah, sure. So, okay.
But some of these we know how to fix, right?
I mean, my statement is that if you want to compute this scaling function, if you want to compute this function, you could just work with this theory. You get the exact functions if you solve this theory exactly.
So the example I mentioned is an example where the fermions care about the structure, the global structure.
Yeah.
Is it clear that there isn't some funny business from the fact that which gauge field it is winds around the Fermi surface?
As far as we know, I mean, of course, for example, the prefactor of the entropy, this prefactor t to the z, that certainly depends on the full size of the Fermi surface. So if you want to get that prefactor right, you have to, do a more careful calculation. But if you want to just compute z or even compute the scaling function, I think you can get away with this theory. That's our claim, for sure. Okay, I'm seeing a lot of, this is too much condensed matter physics for this audience, I think. No. You all want to see some ADS. It's coming, it's coming. Yeah.
Big question. What happens if you make a double weak rotation? You change y to a time coordinate without a space coordinate?
Well, you mean, would that help us understand this theory? I don't think so, but okay. You can do any rotation you want as long as you understand this theory. And then you can rotate back, as far as I know. Okay, so, then let me also mention this Ising nematic problem. As I mentioned, it's almost the same theory, and it is. The only changes are these things. You change A to phi, the Ising autoparameter, and you change this to plus rather than minus. That's about it. Okay, so let's do a calculation. So there's our field theory. So we do the most basic calculation of the photon propagator. So I come in with, here's my photon, the dashed line is A. It couples to psi dagger plus psi plus. I just make a bubble of psi plus, and I'm done, and out goes A. So I evaluate this bubble. I get a factor of NF. NF is the number of flavors of psi plus. So that's just the usual NF counting. Every time you get a loop, you get a factor of NF. Okay, so this is now the propagator of one of the fermions, and that's the other fermion. They carry energy omega plus omega and k plus q. So this literally is just exactly that, inverse of that. And this is the inverse of that, well, the same thing, at different momenta and frequency. So you have to do the integral over k and omega. And okay, so I leave that as an exercise for tonight. Go do that integral. Okay, this is where, this won't be in Preskin and Schroeder. If you want some hint, open up Fedor and Valechka or Mahon or some many-body theory course. I mean, so the only thing you have got to get used to is not everything is gamma matrices and relativistic. You just have to do the integral is a little more complicated. Okay, so if you do this integral, actually it's formally divergent, but the divergent term is proportional to q squared. Okay. So that just gets absorbed into the value of g. So that's why I said g doesn't matter. So this is just some regular coupling, which in fact, in the end, you can just rescale to v1. And so you see, we won't worry about that divergent piece. What we're interested in on the non-analytic piece. So there's one non-analytic piece that goes as mod omega over qy. Okay, qy, remember, is the momentum tangent to the Fermi surface. Oops. It's the momentum in this direction. That's y. Okay, so how do I think? What is the significance of all this? So this is done in imaginary frequency. What does mod omega mean? Mod omega really, when continued to real frequencies, I omega. So in real frequencies, it's just d of q. So this is Minkowski, d of q and omega. That term there is nf over 4 pi times minus I omega over q. So how can I understand this? Well, so this is some imaginary part, so it's some dissipative term in the fermion free energy. Fermion, one loop diagram. So let's try to understand in a little physical way. So here I have my electrons, These are the occupied states, and these are the empty states. Okay. Let me just try to compute the dense. I come in with a photon. Forget about all matrix elements. I come in with a photon and give the system energy omega and momentum q. And I ask, what is the density of states for this system to absorb energy omega at momentum q? So just do that a Fermi-Golden rule calculation. So the phase space for energy omega and momentum q. Sorry. So what's going to happen? I'm going to take an electron which is here inside the Fermi surface and knock it to something that's outside the Fermi surface, and I'm going to give it energy omega. I'm taking an electron from here to there, give it energy omega. So what's the phase space? So you got to integrate over all electron momenta. Now the initial state should be, the initial state should be inside the Fermi surface. So Ek should be less than 0. And the final state should be outside the Fermi surface. But that has momentum q. So that the final state has momentum Ek plus q and energy omega greater than 0. So those are the allowed all sets of transition. I can take an electron from inside the Fermi surface to outside. These are states are occupied, these states are empty, and the energy absorbed is q, and the momentum absorbed is q, and the energy absorbed is omega. Okay, just do this integral. You'll find it's omega over q. Okay, I'll leave that as an exercise. This is an easier thing to do than to evaluate that loop diagram. It's the same thing. So this is just telling you that there's a how much energy can the system absorb at energy omega, the amplitude for the phase space for absorbing energy omega with momentum q. And this gives you a damping in the photon propagator. Okay, so now my photon you've learned that the photon has propagator q squared minus omega squared. That's your photon. Omega goes as q, but now I have this Landau damping. This gives me plus I omega over qy. Okay, so now you can see that this term is basically unimportant compared to this omega, so you can throw that out at low frequencies. So now my photon propagator is something very different. It's q squared plus omega over q, and that's called a Landau damped photon. It's overdamped. It's not really a photon anymore. It's really a composite of many particle hole excitations. It's just totally dominated by the particle hole sector. Okay, and I think that's a good point to stop. So questions, and I'll stop right there.
Any questions?
Yeah.
What happens to the imaginary part when q goes to 0?
Oh, thank you. I should have mentioned here. So you see, this is assuming here that actually mod q is less than omega. It's only valid when q is much less than omega. But we'll see that the characteristic q is always much less than omega. Thank you. Some of you may have, if you've taken a solid state physics course, you may have seen this so-called particle hole continuum, something like this. This is a density of states of excitations of a Fermi surface. This whole behavior is what's happening down here. If you've seen that picture, well, that's what I'm doing. Okay.
Any other questions?
So what I'll do next time is just complete this and show you at least how you get some of the claimed properties of the non-Fermi liquid, and then we'll turn to doing this using holography, or at least our best attempt so far.
Well, then we have a tea break now, and we'll come back after tea for John's second lecture. So.